Hello friends, welcome in this lecture number 3.1a. The title of this lecture is Fresnel Bi-prism and the use of Fresnel Bi-prism to determine the wavelength of monochromatic source as well as the measurement of thickness of glass plate using the theory of this Fresnel Bi-prism. I Dr. Mohan Verma from Department of Applied Physics, Sri Shankaracharya Technical Campus, Bhilai. This is the part of sensitive physics learned with Dr. Mohan Verma. Outlines of this lecture: objectives and prerequisite, Fresnel Bi-prism, its theory, conditions for constructive and destructive interference, and theory of fringes, determination of wavelength of light, and displacement of the fringe in presence of a transparent medium, and finally the summary of the lecture. Objectives: the objective of this lecture is to explain the theory and experimental observation and the application of Fresnel Bi-prism, and I expect from my student to have the knowledge of concept of wave theory of light and basics of interference, law of superimposition to understand this particular lecture. So the introduction of this Fresnel Bi-prism, as the name suggests, Fresnel Bi-prism consists of two right angles prism, each of reflecting angles nearly 30 minutes and 179 degree. This is one angle 179 degree and two angles are 30 seconds. So this nearly looks like just a glass plate. So in actual practice it made from very thin plain glass plate by proper grinding and polishing in it, and requires shape to work as a biprism. So as far as the theory is concerned, here this S is that main light source, and after passing through this biprism, the two images of this light source is generated. So this first light source, after refraction, after refraction, this light come at point B, and the second from the second source, after refraction, this light come at EC. So by taking this refraction part, we get this S1 and S2. So it's a narrow vertical slit illuminated by monochromatic light. The light from S is allowed to fall symmetrically. Remember this should be at the center, means symmetrically on the biprism VP. The light beams emerging from the upper and lower half of the prism appears to start from two vertical images of phase, that is namely S1 and S2. So this S1 and S2, these two images will behave like two different source which is responsible for interference of light, and this is similar to that Young's bi-slit experiment, where that division of wave frontage take place. And this S1 and S2, the distance is taken as 2D, and this distance from this source to the screen is taken as capital D. So further calculation is here. Now the fundamental of this interference, the superimposition of waves. Here these are the S1 and S2, those two images of that source S, and this will behave like two different source, and these two sources fulfill all the conditions for interference, and light start from S1 and reach to P, and light start from S2 again reach to P, and here that superimposition takes place. So we will use the law of superimposition and get required condition for constructive and destructive interference. This is a very fundamental calculation, and the students have performed this calculation in 12th level physics also. So we will take two different wave equations for S1 and S2 and perform some mathematics to see that law of superimposition. So Y1, this is the equation for the first wave. It is equivalent to A1 sine omega t. So amplitude is given here, omega is the frequency, and t is, and the second equation of the second wave is Y2, that is A2 sine omega t plus delta. Here this omega is same, there is no omega 1 and omega 2, because for the interference one of the required condition is its frequency must be identical. So frequency is identical, so we have taken this omega here, and amplitude is similar, so A1 and A2 it is similar, not very much differentiate. Now we will use law of superimposition. So after law of superimposition, y is equivalent to y1 plus y2. So y1 plus y2 is equivalent to the sum of these two parameters. So we will expand this by using simple trigonometrical function. So this a1 sin omega t, the first term, and second term, the term is expanded here as a sin omega t cos delta plus cos omega t sin delta. And now we will accumulate that sin omega t at here, and the second cos omega t here, and then we will have this y is equivalent to, by taking the common, a1 plus a2 cos delta sin omega t plus a2 sin delta cos omega t. Now this is the resultant wave, and we have to convert this wave in similar to this parent wave, and this is in terms of sine. So in order to convert these two waves as a sine wave, let us assume let us take some assumption. So let us have, this is a sin omega t, so we will take this as a cos omega t, and this is the cos omega t, so we will take this as a sin omega t. So r cos theta, it is taken equivalent to a1 plus a2 cos delta, and r sin theta is equivalent to a2 sin delta. So when we put here, this y will be converted as a big sine wave. So in order to calculate this value of r, this is cos term, this is sine term, so it can be eliminated by taking the square of these two and by adding. So r square, it is equivalent to a1 plus a2 cos delta, the whole square of this, plus a2 sin delta square, and sin square theta plus cos square theta, this is equal to 1. And then after just expanding this, we will have this r square is equivalent to a1 square plus a2 square plus 2a1 a2 cos delta. This delta is the phase difference between two waves. And now, so the final form of wave after superimposition is y is equivalent to r sin omega t plus theta, and we have calculated this r as equal to r square is equivalent to a1 square plus a2 square plus 2a1 a2 cos delta. Simple mathematics terms here, and we can also calculate this theta by taking the division of these two. So r sin theta upon r cos theta, this will convert it to tan theta. So tan theta is equivalent to a2 sin delta upon a1 plus a2 cos delta, and when one can calculate that theta. So now we will convert that in terms of intensity, and we know, as far as the wave theory is concerned, this intensity I is proportional to r square, whereas r is the amplitude. So intensity is proportional to, equal to square of amplitude. So here this r square is taken as equivalent to I, that is equivalent to a1 square plus a2 square plus 2a1 a2 cos theta, and this a1 square, this is the intensity of the first wave, and a2 square is the intensity of the second wave. So we can also write this terms in terms of intensity. So now we want to have maximum intensity points. So condition for constructive interference, for the constructive interference, the intensity must be maximum. So this I will be maximum when this cos term, that is equivalent to 1. So this, when this cos delta is equivalent to 1, and this is only possible when this delta is equivalent to 2 and pi, where n is equivalent to 0, 1, 2. This is simple trigonometric function. So when we take this delta is equivalent to 2 and pi, and then this cos delta is equivalent to 1. So the path difference, when this path difference is equal to n lambda, this is the condition for constructive interference, then we will get I maxima. So in terms of I, we will write I maxima, that is equal to a1 square plus a2 square plus 2a1 a2, and here this cos delta is equal to 1. So one can write I maxima is equal to a1 plus a2 square. And one special condition is when we put a1 is equal to a2 is equal to a, then this I maxima is equivalent to 2a square, and that is equivalent to 4 times a square, and this 4 times a square, this maximum intensity is shown here. So these are the pattern, these are the points where the maxima is obtained. So at 0, at 2 pi, at 4 pi, we are getting this maximum. Now for the condition for minima, destructive interference. So in order to get that minimum intensity, we must have this cos delta, that is equivalent to -1. So for the minimum, this cos delta is equal to -1, and -1 is we will get this cos delta is equal to -1 when we put delta is equivalent to either 2n minus 1 pi or 2n plus 1 pi, means the odd function of odd multiple of this pi. So in terms of this path difference, that is equivalent to plus minus 2n plus 1 or 2n minus 1 delta by 2. So we should know the difference, the relation between this path difference and phase difference. So here this delta is actually the phase difference, and we are converting this into the path difference by using that relation between path difference and phase difference. So I minima is equivalent to a1 square plus a2 square minus 2a1 a2, where this cos delta is minus 1. So I minima is equivalent to a1 minus a2 square. Simple geometrical calculation, algebraic calculation. So when we put that a1 is equivalent to a2 is equivalent to a, then the I minima will be equal to 0. And these are the points where that I minima, that is equivalent to 0. So these are the points of destructive interference, and these are the points of constructive interference. And in terms of output, we will get this type of lines. These are known as the fringes, interference fringes of alternate bright and alternate dark lines. And this is the condition for constructive and destructive interference. So in order to get maximum intensity, we must have this delta is equivalent to n pi, n lambda, and that delta is equivalent to 2n plus minus 1 lambda by 2 to get the minimum intensity of that light, that destructive interference. Now theory of fringes. So this calculation is similar to Young's bisect experiment. So in Young's bisect experiment, we take S1 and S2, two light sources, and here also we are taking this S1 and S2, two light sources obtained from as the image of that parent source S at the center of that bi-prism. So we are getting that interference pattern here at point P. So we will calculate the path difference in between the S1P and S2P. So the calculation method is simple. So here there is some in order to calculate this, we take this distance O to P as x, and the second that N to P, that will be equal to, if this is this total distance is d, so this distance will be d by 2, this distance will be d by 2. So we will get this path difference delta is equivalent to S2P minus S1P. So we will use the Pythagoras theorem to get this S2P and S1P. So we will take this triangle S2NP, this is the right angle triangle, and by using Pythagoras theorem we will have this S2P square, it is equivalent to S2N square plus Pn square, and this Pn is equivalent to this x, and this is d by 2, so this is equivalent to x plus d by 2 whole square, and this distance is taken is d, capital D, so this is plus d square. So h2p square is equivalent to x plus d by 2 whole square plus d square. And similarly, in order to get this S1p, we will use this triangle S1MP, and this is also the right angle triangle, and we will use Pythagoras theorem. So S1p square, it is equal to this d square, obviously the same, and these terms, this is Pm square, and this point is x, and this difference is d by 2. So this length Pm is equivalent to x minus d by 2 ka whole square. So we will take h2p square minus s1p square. So by using the simple calculation, we will get this h2p square minus s1p square is equal to 2xt, and just divide this in h2p minus s1p and h2p plus s1p, that is equivalent to 2xt, and this h2p plus s1p can be taken nearly equal to capital D. So one will have this h2p minus s1p is equivalent to x small d upon capital D, and this is the path difference, and that path difference we are getting here is xd upon capital D. So the calculation method is simple, and a student have already done this in their 12th class physics, and we are using the same calculation here for that bi-prism. Now condition for bright and dark fringes. So for bright fringes, we have this delta is equivalent to plus minus n lambda. We have seen this condition, and in order to get maxima. So this path difference we have calculated is x small d upon capital D, and for nth fringe we are taking xn here. So xnd by capital D is equivalent to n lambda. So for nth fringe, xn is equivalent to n capital D lambda upon small d. For n plus 1 fringe, that will be in place of n, we will use n plus 1 here. And if you want to calculate the fringe width, that fringe width will be equal to difference between these two, xn plus 1 minus xn minus 1. So by putting the value here, we will get this fringe different, that is sometimes represented by beta also. So beta or this x bar, it is equivalent to capital D lambda upon small d. So this is the fringe width between two bright lines. Now for the condition for two dark fringes, so if nth dark fringe occurs at P, the wave should interference destructively. So this for the constructive interference, this will be called destructive. And for destructive interference, we have the condition for path difference is equivalent to plus minus 2n. Either one can take plus or minus here, plus 1 multiplied by lambda by 2. So we can take the same x and d upon capital D here and calculate it for xn. So xn is equivalent to 2n plus 1 capital D lambda upon 2d. So we can this is xn, and the next fringe will be xn plus 1. So we will put n is equivalent to n plus 1 here, and we will get 2n plus 3 capital D small lambda upon 2 small d. And if you want to get the fringe width between two dark lines, then we will take the minus of this with this. So we will have this beta or x bar is equivalent to xn plus 1 minus xn, and again we will get the same value where as per the same value of that fringe width as we have obtained in the bright lines also. So fringe width means the difference between two dark lines are equal to difference between two bright lines. That's why in the last slide we have seen that the difference between two dark lines are equidistant between the difference between two bright lines.